group, it's Mrs. Schaus here. We're ready to take a look at section 2.6. We have already done some graphing of functions by creating tables of values, using our graphing calculators, and even considered some graphs of piecewise functions. However, what I want us to consider today is a new way of thinking about graphing where we consider a parent function, we are familiar with many of those already, and transformations being applied to that function. So let's take a look at some transformations. Hopefully some of these will sound familiar based on things that you studied in geometry. All right, we're going to begin with shifts, or sometimes you call those translations, right? Vertical shifts, those are the one, up and down shifts, right? Will change the equation in the following sense. If we have the original function and we add a number, notice it's a positive number, we add a positive number, that's going to cause our graph to shift upward, c units. And if we add a negative or subtract a positive c here, that's going to shift our function down c units. Horizontal shifts are a little bit counterintuitive. If we assume that we're talking about c being a positive number again, this is where we are adding or subtracting to the x itself before the parent function is applied. And if that doesn't sound very clear, I think once we take a look at a couple of examples, it will become more clear. If we are subtracting c, or in other words, adding a negative c, that shifts the graph c units to the right. That's why I'm calling this the counterintuitive variable here, because normally when we think negative in a horizontal sense, we think about heading to the left, right? But in fact, when we subtract c, that shifts the graph c units to the right. And similarly then, when we add c units to x, it shifts our function c units to the left. So you'll often hear me say, oh, x, he is that counterintuitive guy, okay? All right, sorry about that. Let's take a look at graphing the function g of x equals x squared minus 4. I know that the parent function is just y equals x squared, and we understand from a prior knowledge that that's a parabola that passes through the origin. I'm going to try to get a little bit closer to this graph here for you. Passes through the origin, and from that origin would also go through points like 1, 1, or 2. If we square 2, we'd get 2, 4, or 3, 9, and so on. However, since we are subtracting 4 after the squaring has occurred, that means that this is a vertical shift, or in other words, it is a shift down 4 units. So I'm going to take the entire parabola that I sort of envisioned up here, and I'm going to come down 1, 2, 3, 4 units here. And from there, I can go ahead and plot those other points that I would have, for some of you, it might be even convenient for you to actually plot those points. Let's see, 2 and 4, and it was 3 and 9. And think about shifting each of the points down 4 units. That's fine. But I think many of us understand the pattern, sort of the way that the parabola would open. So if our new vertex is from here now down 4 units, from there we would go over 1, up 1, over 1, up 3 more, over 1, up 1, 2, 3, 4, 5 more. And we'll do the same thing on the opposite side since we know we have symmetry. 1, 2, 3, 4, 5, right there. Symmetry for this parabola. So I can draw in a pretty decent sketch without the use of my calculator, without saying, hey, this is just the shape of the curve, but this is, a really good graph with several points here depicting that particular function g of x. All right, let's move on to the next one. One of the things I should be looking at or noting, and maybe I should have written it in the previous example, but is that the parent function, I don't know if you want to call it f of x or if you want to call it y equals, that's up to you, but I'll go ahead and call it f of x equals, and it's just, our x cubed, right? This plus 3 means that some transformation has occurred. So if I'm thinking about, again, what the parent function f of x equals x cubed looks like, and we've studied those. We know that has this shape here, right? A change in not direction, but curvature right there at the origin. Again, you could even plot some points and put the parent function on the graph if you thought it was going to be helpful to you. What I need to think about is what this plus 3 is doing to my curve. Now that 3 is being added to the x prior to the cubing happening. So remember before I had said that this addition or subtraction to the x before the parent function was applied would become more clear when we looked at an example. So that's what I'm talking about. I'm adding this 3 into the x before the cubing occurs. So that tells me that this is not a shift that's vertical. It's a horizontal shift, or in other words, a shift right or left. Remember that our x is our counterintuitive variable. So instead of the plus 3 making us normally think to the right, I'm instead going to be thinking to the left. So this is a shift 3 units left, which means that if I could sort of think about this origin, the place where this changes curvature, as being now here at the point -3, 0. It might be convenient to think about making a table of values for this one, if you were to need, or again, going back to what the original function looked like. I know after 0 cubed giving me an output of 0, 1 cubed gives me 1, so I could think about plotting the point here. And then similarly, if I take 2 and I cube that, 2 times 2 is 4 times another 2 is 8, so I'm normally up 8 here. That means if I move over 2 units from now my point of inflection, I would be heading up 8 units here. And again, I've got that idea of a pattern going on, so I could come back and down 1, and then again, when I'm 2 units away from this, I should be down 8 right there. Again, may not be a perfect graph, but it's a pretty reasonable graph of that parent function being shifted 3 units to the left, with a few points, again, being accurate. All right, let's continue onward here. What about when we combine some shifts? So again, this is a parent function that we're familiar with. I'll write up here, the parent function would be f of x equals the absolute value of x. And we know that that is our V-shaped curve that has a slope of 1 for this particular portion and a slope of -1 for this piece here, and passes through our origin there. But now that parent function is being shifted in a horizontal sense and also in a vertical sense. So it is going to be shifted because of the, there go the lights, sorry about that. It's going to be shifted because of this 2 being added to x, and again, remembering that x is our counterintuitive variable. So it's going to be shifted 2 units, not right, but left. Our vertical shift happens just as we would think it would. Positive goes up, negative goes down. So it's going to be shifted 2 units left, and it's going to be shifted 3 units down. So I can think about, again, taking this vertex of that graph and moving it 2 units left, 3 units down. It's right here, and from there I'm going to have a slope that is positive as I work in this direction. Oh, I'm having trouble seeing this, it's so small. Okay, and a slope that is negative in the opposite direction. Okay. All right, let's look at some other transformations. How about reflections? All right, there are a variety of reflections that we could consider, but for this course we are only considering 2. A reflection through the x-axis and then also the y-axis. If we are reflecting through the x-axis, that's indicative of taking the opposite of the entire function, or the entire equation, if you will. If we reflect through the y-axis, that's when we take the opposite of just the x itself. I want you to think about that for a minute. If you are taking the opposite of x, maybe you've got some point in a graph that sits up here. And if you take the opposite x, instead of being, a positive x like I would have over here, it would now be a negative x. That means that this point would now come over here. Do you view that as a reflection through the y-axis? I'm here, now I'm over here. There's my y-axis, right? And similarly, a reflection through the x-axis, if I'm here and now I reflect through the x-axis, what has changed? The y value has changed. And the y value is the function value, okay? So I want us to recognize that I would have here, whatever this output is, that would be my y, and I would have the opposite y being indicating that we were reflecting then through the x-axis. All right, so for this particular function, g of x equals the opposite of x squared, we're going to think about our original parent function, that is just our graph of y equals x squared. And since the negative x is not in parentheses, it is the opposite of the entire function that we are taking. So it is the opposite y, which means that we are reflecting through the x-axis. That kind of fits with prior knowledge that we have about a function like this, because we know that when we have a leading coefficient, instead of opening upward, the parabola would open downward. Okay, so let me start here. And again, using our typical pattern for parabolas, we're going to come over 1, down 3 more, and over 1 down 1, 2, 3, 4, 5. And I'm going to do the same thing on the opposite side because of symmetry. So there is a graph of our function g of x. For h of x equals the quantity, the opposite of x, being cubed. In other words, the x is, we're taking the opposite of that prior to doing the cubing. That means that with an opposite of x, we're reflecting through the y-axis. So we could think about this parent function, y equals x cubed, and if we reflect through the y-axis, it would start over here and then come down in this fashion. So I'm going to start here, but I'm going to use the same pattern where I'm over 1, up 1. Normally, when I'm over 2 and I cube, I'm up 8, so I'll head up 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to do the same thing on the opposite side, so over 1, down 1. And then when I'm over 2, I'm going to be down a total of 8. 1, 2, 3, 4, 5, 6, 7, 8, right there. And of course, we'll put our arrows on the end. Whoops, that's pretty messy. Sorry about that. There we go. A couple of reflections. Okay. Let's take a look at dilations. That is when we're expanding or compressing. Sometimes we call that stretching or shrinking. Stretching or shrinking happens when we multiply by a constant number. Again, we could multiply the entire function by a constant, or we could multiply the x itself by a constant. When we multiply the entire function by the constant number, if the constant is greater than 1, that is a stretch. And it's a stretch by a factor of c, whatever the c value is that we're multiplying by here. But if c is between 0 and 1, not including, then that is a shrink vertically by a factor of c. I think that kind of, should be, something that makes sense to you folks. If we're multiplying, let's say, by 2, it makes sense that that sounds like a stretch. And if we're multiplying by a fractional piece between 0 and 1, let's say a fourth or a half or 2/3, right? Then we're making the output smaller. So it, again, would represent a vertical shrink by a factor of c. Notice that in these inequalities, nowhere here does it say that c is something that's less than 0. If c were less than 0, then that would imply a negative that we're multiplying by. And if we were multiplying by a negative number, then essentially two different transformations would be going on. One would be associated with the numeric part of C if we took the absolute value. And the second one would be a reflection like we just looked at when we multiply by a negative or take the opposite of. All right, now, again, x is our counterintuitive variable here. So when I'm multiplying x by some positive C value that is greater than 1, it is actually a shrink horizontally, and it's not by a factor of C, but by a factor of 1 over C. That should kind of make sense again, because if we're multiplying, let's say, by 2, and I'm calling it a shrink, it doesn't really make sense to say shrink by a factor of 2, now does it? So it would be shrink horizontally by a factor of a half. And for this next piece, if our C is a fractional value between 0 and 1, not including 0 or 1, then it is a stretch horizontally, and again, it's by a factor of 1 over C. So if you're multiplying by, let's say, 1/4, in order for us to call it a horizontal stretch, we would need to say that it's by a factor of 1 over 1/4, or the reciprocal of 1/4, which would really then be by a factor of 4. Let's take a look at a couple of graphs where some dilation has occurred. So here's our graph of, or our equation rather, g of x equals 2x squared. And in order to graph that, again, it might be helpful for us to think about the parent function. I'm going to try to move this down a little bit so we get a better view. I'm going to put in lights again, an axis here. So there's our y-axis and our x. Okay. All right, our parent function, f of x equals x squared. We know what that looks like. In fact, why don't we think just for a moment here about a table? Not that we necessarily need a table for the parent function, but I'm going to put down some outputs for x squared once I pick some x's. So let's do like -2, -1, 0, 1, and 2. And for the parent function here, if I plug in -2 in square, I get an output of 4. -1 there in square, I get 1. And similarly, 0, 1, and 4. But now what I want you to think about is what happens when I put these same values into our new function g of x, which equals 2x squared. If I square the -2 here, I get 4, and then times 2 more, I get 8. Squaring the -1, again, 1 times 2, I get 2. And similarly here, I would get 0, 2, and 8. And so what I want you to see, since we call this multiplication, which recognize is not to the x prior to the squaring, that would look like this, multiply by 2 first and then square. This is actually taking x and squaring it and then multiplying by 2. So we're multiplying the entire f of x by 2, which means that it is a vertical stretch by a factor of 2. And so what I wanted you to see is that all of these y values, all of these outputs, are now doubled. Yeah, that's a stretch by a factor of 2 if you're doubling outputs. So let's go ahead and plot those points. At -2, I need to be up 1, 2, 3, 4, 5, 6, 7, 8 right here. At -1, I need to be up 2, 0, 0, 1, 2, and 2, 8. And I'll go ahead and graph my function. Okay. On we go to another here where we are going to take a look at a dilation as well as a shift. So let's start out with the dilation. I want to start by thinking about, well, let me actually first real quickly write down the parent function. F of x equals the square root of x. Okay. I want to think about what's happening to that x first. And that is that I'm multiplying it by 2 prior to taking the square root. So that is going to be a horizontal dilation. Is it a stretch or a shrink? Well, again, x being our counterintuitive variable, that means that while normally we think about multiplying by 2 being something that would make bigger or maybe stretch, it's actually, counter to that. So it is a horizontal shrink by a factor of the reciprocal of that, 1/2. We'll talk about how that makes sense in a couple minutes here. After that, I also have this 3 being added, and it's not being added to the x prior to the rooting. It's happening after the rooting, after the parent function is applied. So that is a shift upward 3 units. Shift up 3 units. Okay, let's set the shifting upward 3 units aside for just a minute and think about the parent function and applying this horizontal shrink. So I'm going to start by thinking about the graph of just regular old f of x equals the square root of x. If I plug in 0, the square root of 0 is 0. If I plug in 1, the square root of 1 is 1. If I plug in 2, the square root of that is, okay, well, it's 1 point something, but I'm trying to make this easy for us. So let's plug in 4. The square root of 4 is 2. And the square root of 9 is 3. And yes, if I had plugged in 2 and 1 point something, it would sit here, which is consistent with our graph having this shape. Okay, let's now think about taking some x values and finding the outputs just for the square root of 2x. And I'm going to be strategic about what I pick. I'm going to pick 0, and then I'm going to pick 2, and how about 4.5? And maybe you'll be able to see why I'm choosing those values. If I plug in 0 here, 2 times 0 is 0, the square root of which is 0, that's nice. Why do you suppose I picked a 2? Well, 2 squared is 4, and that's a perfect square, so the square root of that 4 would give me an output of 2. Hey, maybe I should have picked a half here as well, because 2 times a half is 1, and the square root of that is 1. That would have been another nice point to pick. I picked 4.5 because when I double that, 2 times 4.5, I get 9, and the square root of that 9 is 3. So I picked these thinking about how I could get some nice outputs. Let me go ahead and plot those points now. So now I'm at 0, 0, I'm at 2, 2, and I'm at 4.5, and then I'm up 1, 2, 3 right there. Now some of you, if you were trying to graph this, might say, oh, that actually looks like it's taller, like it's some type of vertical stretch. And perhaps that is true, that it has that appearance. But what I want you to see is that for the same amount of rise, I only had to go over half the amount. So where normally I would have said for the parent function, I'm moving 4 units over and 2 units up, now I only had to move 2 units over to travel that same amount 2 units up. Ah, that's how it fits the idea of being a horizontal shrink. So I'm going to deepen that a little bit as well. Yes, it does still extend out. There'd be an arrow on it. So this is my original f of x. This is the function, maybe I'll call it g of x, which is just the square root of 2x. So my final function here, h of x, needs to be shifted up 3 units. So I'm going to take each of the points that I had put in my table here, and I'm going to move them up 3 units. So let's see, at 2 and then 2, I'm going to move that up 1, 2, 3 units. And then at 4.5, I was up 1, 2, 3, and I'm going to move that up 1, 2, 3 more units as well. So those 3 points help me to define my final. I wish this were in color so I could indicate this is my final graph, but I'm going to do that by labeling. That is h of x, my final function. All right, that is where I'm actually going to end this portion of the video. It is not all of section 2.6. We have some other things to talk about with symmetry and also with being able to not only graph when we're given the equation, but kind of the reverse of that. If we're given some information, can we produce the equation? So that's where I'm ending it for now, folks. Have a great day, and I'll talk to you soon.